Good morning, good afternoon, wherever you are, whenever you are listening and watching this. Thank you for joining. This is the keynote for the Cadence Electronic Systems SIPI Forum. And I will be talking about, is power integrity really the new black magic? So in a keynote talk, people usually expect four things. Some kind of overview of the past, reflection, certainly predictions for the future, big picture with personal stories, and some humor. Now, this last thing is the one that I cannot promise because I'm not a good joke teller, but I will do my best to give you the other three. So, let's start with a reflection on the past. It was in the early 90s that, in terms of a principle, we still just had electromagnetic compatibility, EMC. And it was in the very early 90s when signal integrity as a discipline was born. And most famously, Dr. Howard Johnson coined this black magic in the title of his book, which is still a bestseller in these days. When we look at the transition between electromagnetic compatibility and the signal integrity, my take is that Dr. Clayton Paul's book was probably the forerunner, at least for me personally, which appeared in 1993. It was called Introduction to Electromagnetic Compatibility, but it was really speaking about most of the things that became the foundation of signal integrity later. And it was not until the early 2000s when power integrity as a discipline became more widely accepted and practiced. Of course, these dates are not, hard dates. Things evolve gradually. Power integrity was already included in Dr. Clayton Paul's book. It was just not called with that name at that point. So, signal and power integrity can impact every walk of our lives. For instance, what I'm showing here, that's an example that I personally lived through in 2003 when there was a huge blackout in the North American continent on the East Coast. And if you go to the Wikipedia pages, which are quoted here on the slide, you can learn, in case you didn't experience it yourself, you can learn that it was starting as a signal integrity issue, overloading a section of a household transmission power line. It got disconnected by the protection, but if we disconnect a transmission line carrying current, it will create a voltage spike. The voltage spike traveled down the unconnected side and tripped over voltage protection, and that created a chain reaction, which certainly could have been prevented by a different organization of the grid, but this is what it was. And this pretty much wiped out most of the East Coast power grid. On the two photos you can see side by side, what was from the sky the east coast of the United States the night before and the night of the blackout. So this was a very visible event of signal and power integrity failure, which impacted millions of people. Now, the PDN trends over time is that we have to deal with an increasing number of independent supply rails. In the very old days, personal computers had just one silver box with a 5-volt supply output and maybe 12 volts for the hard disk, and that was all. In these days, we have to deal with dozens and dozens of independent supply rails, which also means that assuming the same physical envelope for the system, we have less room for each supply rail. But not only that, we want to cram even more things into the same space. So not only the independent supply rail number is going up, just the overall density also increasing and the system speed. Now, it is true that as we make circuit loops and the physical circuit smaller, that will help increasing the bandwidth of the circuit and reducing the coupling between adjacent circuitries. However, when I tried to look at different designs decades ago and then today and try to estimate what the future holds, we can predict and notice when we look at past data that beyond the scaling, unfortunately, we are putting things much closer than how much we shrink them. So this means that both in signal integrity, but also in power integrity, the absolute noise keeps going up, even though the sensitivity of the circuits may be higher and higher, so they do not tolerate that easily noise. And then we all want higher efficiency because we burn more power in our systems. We want to do that efficiently. So higher efficiency comes with lower losses in the power path, but lower losses inevitably mean lower resistances, less dampening of any kind of parasitic resonances. So that higher parasitic resonance and higher chance of ringing is one thing where CAD tools could help customers to improve the designs. This is certainly a two-way street. We need good models, and that's not the CAD company's responsibility, but we definitely, as users, expect the CAD companies to work with those companies which create the models so that the integration and the usage is seamless and painless. But lastly, the last point on this slide is that the size and cost constraints are becoming more pressing, meaning that we would like to achieve the same functionality in a smaller overall volume, and we would like to achieve it at a lower cost. So all of that make it even more important to suppress resonances, where again the CAD companies can help us with accurate predictions. So traditionally, when all three disciplines already were, I would say, acknowledged and practiced, signal integrity, power integrity, EMI, electromagnetic interference, another acronym for electromagnetic compatibility. So these three at first in the early 2000s were typically practiced by different individuals and different groups. But that doesn't work anymore in these days because the impact of these disciplines on the system are intertwined and the interrelations cannot be ignored. Like we could bring up a lot of examples when signal integrity failures may impact also electromagnetic compatibility. Power integrity failures may show up not on the power consumer side as a failure, but EMI failure. And the list could be continued with a lot of actual practical examples. And in the longer 5-day courses, we can go into a lot of these details. But overall, the summary here is that the in-system interactions and the in-system electromagnetic interference is becoming a problem. And before Hauer-Johnson called signal integrity black magic, the practicing logic and board engineers called electromagnetic compatibility the black magic. That is certainly challenging with all of the three-dimensional distance effects. So that is another area where CAD companies could help us with faster and more detailed tools. It is certainly some areas where I personally feel that the integration is a little bit lacking with other tools. So what are the key challenges with PDN designs? Well, people who do practice PDN designs, they know that on top of everything is the functional specification, the system spec, system requirements. So someone comes up with a product idea and that is defined, is described, it is well known and understood in the sense that people have a marching order, that's what we want to achieve. And of course, in these days, if it's a high-speed system, signal integrity becomes extremely important. So that comes as a supporting layer below the functional specification. But on the bottom, below all of this, are the other supporting functions like thermal electromagnetic compatibility and power integrity. And unfortunately, power integrity is on the bottom in multiple senses. It is on the bottom mostly because in a typical design flow today, the power integrity design comes as the last element in the thought process, which many times means that it's almost like an afterthought, or people may not realize problems and bottlenecks until it may be too late to change. It is also on the bottom in the sense that it is probably the most important of the supporting functionalities, because if there is no clean usable power for the devices, then we can't speak about signal integrity, we can't speak about system functionality, nothing will work properly if power fails. But it is also on the bottom, and that's the biggest problem for the designers, it's also on the bottom in terms of support. And support is a generic kind of a notion here. Support could be like, let's consider signal integrity. Signal integrity has standards, has standard signalings. Signal integrity has a lot of supporting function already worked out by CAD companies, by silicon companies. So the designers can rely on a lot of supporting functions that the common wisdom of the industry already created. When we look at power integrity, unfortunately, almost none of it is present, other than the good thing is we do have fairly good power integrity simulators, but we do not have standards to adhere to. Most of the requirements for a system power integrity design have to come from the system designers themselves. So in that sense, that's a huge challenge. And of course, we could speak about the pros and cons and reasons why it is this way. One reason is very clear. Power integrity is the newest of these disciplines. So we haven't had enough time collectively in the industry to work out all of the details. But I think, in my view, there are underlying fundamental reasons why power integrity can never have the detailed support in terms of standards and helping functionalities that signal integrity enjoys. But certainly this leaves a huge room for CAD companies to give us better tools, at least to analyze what we think our design will be. So this already tells us why power integrity is so difficult, but let's just summarize it in a different way. So power distribution network is a system-wide network present everywhere. What I mean by this is that contrasting to signal integrity. In signal integrity, even today when we try to bring in silicon receivers and silicon transmitters into our complete end-to-end modeling, but through the silicon logic, we usually don't consider signal integrity. We just look at lanes end-to-end, including probably the silicon receive and transmit layers as building blocks. But in power integrity, making this kind of segmentation is not completely safe and doable, because our power converters and power filters are not completely isolating one segment from the other. So it is not only present physically everywhere in the system, but to some extent, everything is connected to everything else. Of course, just in a secondary way, but increasingly those secondary interactions cannot be ignored. It is also clear that power integrity has multiple roles. We have to supply not only clean power to the silicons, but also have to maintain the proper return path for the high-speed signals, and that's typically done in a printed circuit board or in a package by the planes, which normally we also use for carrying power. And then at the same time, if we have any kind of resonances in the power system that may impact electromagnetic compatibility requirements, so we have to watch all of these different functionalities to make sure that the system as a whole will function properly. But probably the most important, and might sound the most controversial here, is the third bullet, stating that In this context, at least, signal integrity is a one-dimensional problem. What I mean by this is that in signal integrity, when we do a design, the signal integrity designer knows the signals, that's the starting point. So the signaling levels, frequencies are known, or at least we have a good target for them. And the signal integrity designer designs the path where the signal will propagate. We design the traces, we select the connectors and the cables and the package traces and the vias. So pretty much the entire path where the signal we hope will propagate is known. It's not a straight path, so of course we have terms and vias and all sorts of three-dimensional features. In that sense, yes, signal integrity is heavily three-dimensional for very high speeds, but in the sense that we know where the majority of the signal should go, it is a line, not a straight line, but it is just a line, and everything else, discontinuities and crosstalk and simultaneous switching noise are secondary effects that we would like to minimize. Contrasting this to power integrity, where could we use traces to carry power? Yes, but common wisdom tells us that today that's not the most efficient way of making a design. We use planes, we use puddles, we use white traces as a minimum to carry power. So that is at least a two-dimensional structure. So when power noise hits the power distribution network, it means that it can propagate at least in two dimensions. But when we consider the multiple layers in a PC board or in a package, most likely it is a 2.5D, if not three-dimensional problem, in the sense that it can go in any direction in the system where we have conductors. But the last 2 points are equally important here, because on top of all this, we meaning designers of power distribution networks, typically have very little input data as a starting point, how much noise we have to deal with on the power supply. Quite clearly, for most of the PDNs today, we want to carry DC. And we would like to block AC as much as possible. But exactly the AC part on the excitation side is highly unknown in many of the situations. And here, when I think about how CAD companies could help us, certainly the data has to come from the maker of the device which creates the noise. But coming up with standardized ways of describing it, that's where I see huge openings and huge possibilities for CAD companies. A good example where Cadence championed it was the introduction of IBIS version 5 about 15, 16 years ago, where IBIS was turned into a power-aware version of IBIS, and it certainly could be refined. But this is all convoluted with the last bullet point that, as I mentioned on the previous slide, basically the metric, what we need to achieve, is fairly tricky to define. And here we don't have time to go into the details of this bullet item. We just have to keep in mind that it's not a straightforward thing. So when now we turn to predictions, I would like to quote here Roy Amara. He lived in the 20th century, was born in 1925, and he was the president of the Institute for the Future. And he is mostly remembered after his law, what he formalized, like shown on this little sketch. Humans, in terms of time, tend to think linearly when we think about changes, but technology typically changes non-linearly. At the beginning, when something new comes along, usually it takes hold a little bit slower than people would like to happen. At the same time, when the critical mass, when all of the critical things are in place, things will speed up, and longer term, the cumulative effect is typically way faster than what humans can think of at the very beginning. So with that in mind, when we try to think about trends, what I'm showing here is a summary of CPU, or today it could be a GPU or any big chip which has a lot of logic in it. Over the past 30 years, how the typical clock frequency, power consumption, current consumption, typical supply voltage, and the resulting target impedance for feeding the beast, how these changed. And please notice that the time scale is linear, but the vertical scale in MSVA units, actually, in case you want to assign actual numbers to all of them, the vertical scale is logarithmic. We can see that the target impedance for people who do the power distribution design in the frequency domain, the target impedance drops decades and decades of values. And right now, for really big chips, it is approaching single digits of microohms. Just 20 years ago, single digits of milliohms was extremely challenging to achieve. The industry figured out how to do it, but something, 10, 20, or single digit microohms power distribution will call for a different paradigm of how we design power distribution networks, how we simulate it, because so many minuscule details which didn't matter for higher target impedances will come to the forefront. And that is another area where CAD companies probably have a lot of runway to help the designers better, to include more details and more features. And I will have a few more words about this thought just in a few minutes. So here is a personal reflection. Years ago, I was asked by a component company to give a keynote talk at their business meeting. And when I asked about suggestions and inputs in terms of what I should speak about, the suggestion was that yes, if you would like to include technical details, of course, but ultimately what we would like to know, how much of our components the customers will need longer term. So I looked around, checked the past history, and looked at the process, how we design power distribution networks, and came up with this simplified sketch, which is shown on the bottom of the slide, which again deals with this in the frequency domain. Not to say that frequency domain is the only way to approach this, but most of the models we use are linear anyway. So for linear models, the domain doesn't really matter, whichever is more telling for us and easier to understand. So let's say vertically on the scale, we have impedance of the pieces of the power distribution network, and horizontal axis is log frequency, so it's a Bode plot. The heavy blue line on the left, that's a sketch how we can illustrate the impedance of the DC source, whether it's a battery or linear regulator or switching regulator. It has a low frequency DC resistance, and then it goes eventually inductive. And then on the right, illustrated by the heavy green line, we have the impedance of the packaged silicon or any other semiconductor, whatever we want to feed. It has some built-in capacitance, either by the natural device capacitance, or maybe in the package we have purposely added package capacitors. So those two heavy lines create this tent-like, tent-shaped impedance profile. If this is hit by a transient noise current, the question is how much noise voltage we will get. And here we have a branching of the answer, because it could be that the transient noise of our circuitry will not excite at peaking, and then nothing bad happens. Maybe we do have spectral components in that frequency range, noise is generated, but the circuitry can tolerate that noise. Again, nothing bad happens. But if we come to the conclusion that too much noise would be created if the transients, which will contain, in that case, sufficient energy in that frequency range, would generate noise which is too much, then we have to add bypass capacitors on the connection, which is our printed circuit boards, and that is the dashed orange line. So how many bypass capacitors we need, just visually, simply depends on how good DC sources we have and how demanding consumers like packaged silicon or semiconductor circuits we have. In the very old days, illustrated on this slide, in the very old days, we didn't need any bypass capacitor, and the circuits were working perfectly well. What you see here on the slide is a photo of an old computer board that I still have, and I carry it with me to my courses, and I hand it out to the audience so that they can take a look. It's a DTL, diode transistor logic. It was a simple gate. You can see the white little glass encapsulated diodes on the bottom. You can see the green carbon resistors, and you can see the vertical standing shiny metal transistors, and also the horizontally lying down black painted secondary layer of transistors. But you don't see any bypass capacitor here. And it was working okay. And we can also point out that if we look at the power distribution itself, on the lower right corner of the board, you see those two shiny fingers. That's where power came in, power and ground on those two edge fingers. And if you follow the photo and you can see purposely the way how I made the photo that you can see the shadow of the backside. This was a simple 2-layer board. We can follow the entire path of the power distribution. It's just a wide trace with absolutely no bypass capacitor, and it did work. Fast forward a few years. This is on the left, lower left, the first CPU module that I was working at some microsystems in 1997. It had 2 CPUs, 16 DIMM slots. The footprint size of it was 20 inches by 8 and 5 inches, and it had 1901 capacitors on the board, feeding all that electronics, a few hundred watts total consumption. On the right, it is a newer board from Oracle. The last Spark M8T8 CPU module that I was involved in the PDN design. You can see on the top side in the center of the board, the big shiny piece is the silicon with its package around it. On this board, there is nothing else, just power distribution components. That's the only and sole purpose of this board, 6 inches by 5 inches. And to feed this single CPU, it took 637 capacitors. So another prediction from the past, I think I got it right. I'm not 100% sure, but I think I heard it in the 1995 DesignCon keynote. And I still remember almost word by word what was said. In 10 to 20 years, computers will look like hairy, steamy golf balls. So this has 3 predictions, that computers will be hairy, referring to the fact that back then in the early 90s, still a lot of parallel cables were hanging out of the computer boxes, assuming that the number of peripherals will go up, which did in fact happen. The assumption was that the computers will have a lot of cables hanging out of the boxes. The next prediction was it will be steamy because it will generate so much power that it will be extremely hot. And they will look like golf balls because we can miniaturize things and it will be very tiny. Well, there are different reasons why these predictions, not all of them happened. One of them, namely that computers are getting hotter and hotter today, that is true and that has happened. Another couple of predictions from the past, and just reflecting also on the process and trends, to help the power distribution move closer to the targets, integrated voltage regulators are becoming common. And since that on a wish list was already there for decades, I'm just illustrating it with one of my old slides that I made in April of 2000, showing a concept package where next to the silicon were the DC-DC converters. Luckily today it's all doable. Back then, year 2000, it was just a dream. The next few years certainly we'll see further applications of this exciting, very good possibility. And this is again where CAD companies could help us tremendously by working with DC-DC converter vendors to refine their models, which is certainly again not the CAD company's responsibility, but the CAD companies are the first line users of the models. making sure that the end user, the PDN designer, can use them efficiently, that would be a huge help. We can also predict that the allowed noise voltage, the voltage band set aside for noise, will keep shrinking. We can also predict that the trend will continue on loosening component tolerances, not on purpose, of course, because there are a lot of things where we would like to see tighter tolerances. The issue is, the more and more we move to miniaturized components, the natural tolerances, as we move to a few nanometer nodes, things become more highly statistical, which brings me to the bullet item here, that designing for the worst case may not make sense anymore for a lot of the systems in the future, because if I want to make a system which for sure under all of the circumstances will function properly, it means that I have to throw away a lot of the systems which might be 90% okay, but otherwise would not survive the worst case test. And of course, it depends on the application, because in mission critical applications, and one of the coming slides will come back to that, we don't want to allow that. But there are a lot of applications where failures here and there are accepted by the user. So individually characterized systems may appear gradually also in the mid and higher end system. And that brings me to the reliability point, because reliability becomes more and more important because we use more components for power distribution. And the photo is just a simple reminder that it's always the weakest link that fails. This photo was taken at a traffic light under which I was traveling before the pandemic every single day. And I watched the traffic lights replaced from incandescent lights a few years ago to LED lights. And the LED lights were nice and shiny for a few months, and then gradually here and there black spots appeared. Did the LEDs fail? I highly doubt it. It's not the LED that fails in this circuit. It is most likely the driver or any of the supporting circuitry. So making just one element higher reliability is not enough. It's common sense, we just need the reminder. And it will be even more important for autonomous vehicles. And here I'm borrowing two slides from my friend, Professor Todd Ewing. He did a keynote talk at DesignCon 2018. And just two slides tell the point that I want to make here, that in these days, in the US alone, yearly 30-somewhat thousand fatalities happen because of car crashes, and most of them are blamed on the driver, probably rightfully. And if the expectation is that replacing the human driver with electronics and machinery will eliminate the fatalities completely, that's what Todd's slides illustrate. It may not be that easy, because even if we take electronics with reliability, which today exists only in military and space electronics, even if we do that, we could still expect probably 300 fatalities just caused by failures. In this case, it would be the electronics itself. Is that acceptable? Well, it all depends on how we view these things, and the jury is still out. where the CAD companies could help us tremendously, helping the designer to bring reliability into the design process. And this brings me to the last effective slide here before the summary. On the right, I am showing a 50-year-old little homemade DC-DC converter that I made as a high school student, not knowing much about electronics. I didn't have any oscilloscope, just a simple voltmeter. And it was built, it was working, and you can see the photo to the left of the schematic sketch. It supplied a tiny 30 milliwatt power. And you can also see the measured dimensions. The dark spots are not dirt on the body. It is just how the light is reflecting on the galvanized metal shielding case. Fast forward to a few years ago, in the middle of the bottom of the slide, you see one interseal encapsulated DC-DC converter, which can output 100 watts approximately maximum. And you can see that it's probably 1/8 of the volume that 50 years ago took, for 30 milliwatts. So we definitely will see a continuation of miniaturization. Battery technology for autonomous vehicles will improve. The jury is still out with the gallium nitride silicon carbide battle. A high voltage, high power conversion circuits will improve. And the big item is reliability. It must and hopefully will improve, giving a lot of opportunities for CAD companies to work with the vendors supplying models, incorporating them in a way that users can enjoy the benefits. And behind all of this, the driving forces will be green energy and autonomous vehicles. So as a summary, the PDN focus will shift a little bit away from board designs, more to source and load improvements. The technology improvements, the big items where I see major things happening are the battery and power conversion circuitries. And we have to be prepared that the system density will increase and will drive up in-system interference, again, giving a lot of opportunity for CAD companies to help us better with tools to predict that. And the same is true for reliability. It will and must improve. And that's all I had for this keynote. Thank you very much. And I believe we still have a few minutes for questions in case anyone has comments or questions. Thank you for joining.